In this video, we're going to introduce the topic of definite integrals. So let's start with some theory. If f of x is continuous on a closed interval ab, or piecewise continuous on a closed interval ab, then f of x is integrable on a closed interval ab. Therefore, the definite integral exists and is given by integral a to b f of x dx. So here in this diagram, we have a function that's piecewise continuous, and you can see how parts of the function is above the x-axis and parts of the function is below the x-axis. So the integral a to b f of x dx is a net area, which means area above the x-axis minus the area below the x-axis. So the integral a to b f of x dx is equal to a1 minus a2 plus a3. And this is the geometric idea behind it. And you can see that clearly from the diagram that the integral a to b f of x dx is basically going to be a1 plus a3 minus a2. So let's go over another theorem. If f of x is integrable on ab, then the integral a to b f of x dx is given by the limit n goes to infinity, summation I goes from 1 to n, f of x delta x. We're going to introduce the theory of a definite integral for right hand, left hand, and midpoint Riemann sums. So here we have a diagram, and we divide the interval ab into n equal subintervals. And that's given by delta x is equal to b minus a over n. So the first starting point is x0, that's a, x1, that's a plus delta x, because we're going up by equal partitions. x2, that's a plus 2 delta x, x3, that's going to be a plus 3 delta x, xi is going to be a plus I delta x, and xn, which is your last x value, that's a plus n delta x, and that is b. So the right-hand rule is given by this Riemann sum, Rn, that's f of a plus delta x times delta x. That is basically the area of the first rectangle. And f of a plus 2 delta x times delta x, that is the area of the second rectangle. And we add up these rectangles, and the very last rectangle is going to be, the area of the last rectangle is f of a plus n delta x times delta x. And this expression represents the area of this last rectangle. And so we're basically adding up these rectangles. And this represents the Riemann sum, the right-hand Riemann sum, with n rectangles. So let's just put these in. All right, so this is the basically right-hand Riemann sum. We're also going to look at the left-hand Riemann sum and the midpoint. So when you take the limit as number of rectangles n approaches infinity, the limit of Rn as n goes to infinity is going to give you the limit of the Riemann sum, summation f of a plus I delta x times delta x, and that's the definite integral a to b f of x dx. This is known as a right-hand Riemann sum, and you can see that in this case, as n goes to infinity, these extra beds, these rectangles, the extra beds will disappear, and you get the exact area under the curve. In fact, in all cases that happens. So as the number of rectangles approaches infinity, then the Riemann sum becomes the exact area under the curve. The left-hand rule is we basically, on every interval, we choose the left endpoint. So it's going to be f of a plus I minus 1 delta x times delta x. That's the left-hand Riemann sum. Let's go back to the diagram and show that. So I'll color it in a different color, let's say red. All right, so left Riemann sum, that's going to be like that. In this interval, we choose a left-hand point. In this interval, from x1 to x2, we evaluate the function at x1. And in the third rectangle, we do the same. And let's add up these rectangles. As you take the limit, of course, it gives you the exact area under the curve. So in the limit, the Riemann sum becomes the definite integral. We also have the midpoint rule, and the midpoint rule evaluates the function at a plus I minus 1/2 delta x. That's basically creating the midpoint. So let's go back to the diagram and see if we can kind of show that. So the midpoint is going to be, let's do that in orange. It's going to be like that. Evaluate the function at this point, at this point, at this point, at the midpoint of every interval. At this point, here, here. Let me draw it for one of these rectangles, just so you've seen that. So here it is. And the midpoint rule basically evaluates the function at the midpoints of every rectangle. So these are the different Riemann sums that you may encounter in questions. And the most common one that you'll see is a right-hand Riemann sum. Sometimes you'll see the left hand as well. And at times you may see the midpoint Riemann sum as well. So let's just summarize everything. Delta x is equal to b minus a over n. That's basically the width of every interval. The right-hand point is xi is a plus I delta x. That samples the right-hand points, and the left-hand point is xi minus 1 is a plus I minus 1 delta x, and that means you're choosing the left-hand point of every interval, and the midpoint evaluates the function at the midpoint. So the midpoint is x midpoint is a plus I minus 1/2 delta x. So there it is. Thanks.